Welcome back to MLT 115. In today's lecture, we're going to be discussing spectrophotometry. In today's lecture, we're not only going to be discussing how spectrophotometry works, but we're also going to be discussing Beer's law and why it's important to lab science. Here's our objectives for today's lecture. You can read through these on your own. The first piece of information we need to be aware of is that electromagnetic energy exists in waves, and we need to understand the concept of a wavelength. A wavelength is the distance from one wave to the next, so that's represented by this arrow here. Okay, and sometimes you'll see wavelengths represented by a Greek letter. This Greek letter is lambda. Sometimes you'll see lambda written as it's illustrated here, or sometimes you'll see lambda illustrated like this. So you'll notice along this whole wave there are peaks and there are low points. Well, all the peaks are known as crests, and all the lower points, or the lowest points, are known as nadirs. Along this electromagnetic wavelength spectrum, we have different groupings of wavelengths. We have a grouping of ultraviolet light, which is 100 to 400 nanometers. We have visible light, which is 400 to 700 nanometers. And we have infrared, which is 700 to 900 nanometers. So everything that we're looking at as far as our wavelengths are measured in nanometers, and the actual one that we're concerned with, or the grouping that we're concerned with in lab science, is the visible spectrum of 400 to 700 nanometers, because that's where most of our specimens are going to fall. They're going to fall in that visible light spectrum, and all the colors for that spectrum fall in the Roy G. Biv, the red, orange, yellow, green, blue, indigo, and violet spectrum. And that's what this is showing us here on this chart, is all those colors in the visible spectrum. And again, these are measured in nanometers. So why is all this important to us in lab science? Well, different specimens or different substances can absorb or transmit light at different wavelengths. So when we're trying to detect what a specimen is or how much of a specimen's there, it can make it possible to detect how much, or if a compound is there, using light. Remember, a whole series of wavelengths is called a spectrum. So let's look at this chart. On one side, on the left hand side here, we have absorbance, and down below we have wavelength. Remember, in lab science I said we're usually going to be looking in the visible light spectrum, and we're usually going to be looking somewhere between 400 and 700 nanometers. So this is going to be in nanometers down here. So whatever substance we're testing, it looks like it's going to have peak absorbance. The arrow is pointing to peak absorbance at about a little over 600 nanometers. So that's going to tell us a lot about this substance, of how much absorbance it has at what wavelength. So you could take this information about absorbency at this wavelength and interpret something about the substance that you're testing, whether it be the concentration, maybe help narrow down the identity of the substance. You could get a lot of information as a lab tech from the data collected from this type of information. The type of instrument we use in lab to give us this type of information is a spectrophotometer. It can give us the results of absorbency or the amount of light transmittance. Now let's discuss how a spectrophotometer works. The first thing you need is a light source. So you're going to have light going in to your sample. Okay, then you're going to have some kind of a filter or prism that your light's going to go into before it hits your substance. And your substance is going to be in some kind of little cuvette or the little container that holds it. And usually the cuvette or container are square or rectangular in shape, depending on the model or brand of your spectrophotometer. But your test substance is your sample, your patient sample. So your light from your light source is going to hit your sample. So here we're going to see how much light is actually going to transmit through our sample to the other side. Okay, so we're trying to see how much is actually going to get through to the other side. So how much is going to transmit through. Then the detector is going to detect how much light actually made it through the sample to the other side. And it's going to give us a signal, or give off a signal of exactly how much light made it through. And that signal is going to be displayed on the display of the spectrophotometer. And it's either going to be displayed as percent transmittance or absorbance, depending on how you have your spectrophotometer set up. So you will have a numerical value on your display, so you can take that numerical value and interpret your results from the spectrophotometer. The only other thing I want to point out on this slide before we move on is this little ratio of T equals LT over LO. And T is our transmittance, LT is over LO, and LT is our light, transmitted light, or the light that made it through our specimen, and LO is the incident light, or the light that we had before it ever hit the sample. But we'll talk about this ratio a little bit more on a slide coming up here in just a minute. I want you to be able to see exactly what a spectrophotometer looks like. This is the little door area where you would open up the lid or door and load your specimen. You would do all of your settings over here to determine what wavelength you want to read out. Again, we're probably going to set it to our visible light spectrum. Somewhere's in between 400 and 700 nanometers. Also, we're going to tell it whether we want it to read out in percent transmittance or we want it to read out in absorbance. So all that stuff can be done here on this side of the spectrophotometer. But when you open this door or lid up, it will look like this over here. You see a lab tech actually loading a sample cuvette. So the sample's already inside and they're loading it up in the little wells in order for the spectrophotometer to read the sample. There will be a light source in here somewhere. The light source will shoot towards the sample, and depending on how much light either the sample absorbs or how much actually is transmitted through, the spectrophotometer will give a readout of a numerical value which we can use as a result and interpret. One of the tests that we use in hematology that we use the spectrophotometer for is hemoglobin. Like I said, we were going to look at this ratio a little bit more for transmittance. T is representing transmittance, and LT is representing the test solution, and this is the light that's being passed through. Okay, the light that made it through the solution. So basically the light that was not absorbed by the substance. Okay, LO is relative to the incident light. So this is the light that was originally shot at the sample. So if you remember, we have our LO going towards our sample. Let's look, that's our sample. and then LT is what's going to come out on the other side. But we want percent transmittance as our answer. Percent transmittance. In order to get percent transmittance, we're going to have to multiply by 100. We're going to multiply this ratio by 100. So we're going to have to take our LT over our LO, multiply it by 100 to get our percent transmittance. And luckily our spectrophotometers are set up where they can do this calculation for us. So our displays, when they're set up to read out as percent transmittance, they will already read out as a percentage. So let's talk about absorbency of a less concentrated solution versus absorbency of a higher concentrated solution. Let's look at the two examples given in the image. The top one is of a less concentrated solution. So this one's less concentrated. And the bottom one is more concentrated. And I was able to tell this best by looking at the color of the two substances. The top one is a lighter color and the bottom one is a darker color. So something we need to know about absorbency. The more concentrated a solution is, the more light that it will absorb, so the less light that will be transmitted through the substance. So if that's true, which of these two samples is going to have less light transmitted through? It's going to be this one, because it has a higher concentration, so there's going to be more light that's initially absorbed from the light source, so less is going to travel through to the end. So in a substance of higher concentration, there's going to be less transmittance, percent transmittance, but the absorbency is going to be higher. More light's going to be absorbed initially. On the other hand, with a substance of less concentration, not as much light's going to be absorbed initially. When your light source is showing through, there's not going to be as much concentration to catch and absorb that light, so your absorption is going to be less, and more light's going to make it all the way through, so your transmittance is going to be higher. Now we need to define Beer's law. Beer's law states that the concentration of a chemical solution is directly proportional to its absorption of light. Another thing that we need to remember is that Beer's law has a linear relationship when it comes to absorbance and concentration. So make sure you remember that it has a linear relationship when it comes to absorption and concentration. Also, we can represent Beer's law using an equation. T equals 10 to the superscript negative A, B, C. A is the constant, B is the path linked through the test substance, and C is the test substance concentration. And we're going to be manipulating this equation around a little bit in order to solve for percent transmittance or absorbency. This is really the only equation or formula that we're going to use in this section to do calculations. All the other formulas are just for illustration purposes and for information purposes. You're going to want to make sure that you have the log key on the calculator that you're using for this class, because when we go and solve these equations, we're going to be putting them in the calculator to solve for either absorbance or transmittance. So the equation that we just looked at has a log in it. If you've never worked with an equation or never worked with log before, log is just another representation for logarithms. And logarithms are nothing but another way of expressing exponents. So like I said, we're just manipulating this original equation of T equals 10 to the superscript of negative ABC to A equals negative log T, and this is the formula we're actually going to be working with and plugging into our calculators using the log key to solve for either A, which is represent absorbency, or T, that's represent transmittance. Now you can go on down. The T is representing our 10 to the subscript of ABC in the equation. But again, this is just more for information purposes. And still work your way on down. You're trying to get your A, B, C by itself. And we're going to go on to. Then we have the final manipulation of A equals ABC, where A represents the molar extinction coefficient, B represents the path length, and C represents the substance concentration. On this final version of the equation for Beer's law, make sure you know what A, B, and C represents. You won't have to solve any mathematical problems using this version, but you will have to know what A, B, and C represents. This is just to let you be aware and know that Beer's law may be represented or presented with varying letters, but it's all the same formula. So these are just some examples. Of course, we're using the one using A equals ABC, but you may see some other text or online where they're using other letters or symbols to represent the same thing. These are all the same formula. Colorimetry is a numerical description of colors. So we can get a readout of a color change or a reaction on a spectrophotometer. So we can also use Beer's law in colorimetry. We're taking out the subjective result of a color change and replacing it with the quantitative result, actually getting a numerical result for colorimetry on a spectrophotometer. So when we're looking at the two variations of Beer's equation given on this page, we've got subscripts of S representing standard solutions. A standard solution is a solution of known concentration. And we also have a formula or an equation representing unknown solutions. And the U's or the U subscripts are representing unknowns. So we could use our spectrophotometer with the concept of colorimetry if different substances, whether it's an unknown or a standard, if they have different colors, we could run them, and if it's a standard, we would know what they should come out, or their results should come out looking like. If it's an unknown, we could use those results to kind of determine what the substance is. This concludes this lecture on spectrophotometry. I hope you got a better understanding of how spectrophotometry works and why Beer's law is important to lab science.